In this video, we're going to look at more into probability. Before we look at more probability ideas, let's talk about this idea of Venn diagram. The Venn diagram can help us understand some of the formulas that we're going to see. So this may be a review for some of you. If you've never seen it, that's totally fine. We're just going to quickly talk about what a Venn diagram is. So in Venn diagram, usually we have this big box, which refers to universal set. Everything that we're interested in, it belongs in this universal inbox. And E, we can refer to an event. Again, we don't have to use an alphabet E, we can use A, B, but this is referring to event. So for example, people who are taller than 6 feet, 6 foot tall, can belong to this group. And anyone who's not 6 foot tall can be in this box, but still outside of the circle. So that's how Venn diagram works. So one important idea here we can discuss is the event E, we can think as this circle contains all the possible outcomes for event E. So sample space for E. Plus anything not E. So let's write not E. If you add those two things, we get everything, U. And in probability, we have a symbol for not E, anything but E. So that's E plus, we write E complement. And if we add all those things, we get U. And we can shade it to talk about that. So let me shade first event E. So here's event E. And if I want to add everything that is not E, let me shade it with another color. So then if I add E, and let me actually write E complement is right here, outside of E. If I add these two things, I get universal everything, U. So we can also apply this in context of probability. In probability, what we think about is probability of E occurring, plus probability of E not occurring, is universal probability, which is 1. Either E will occur or not occur. And all those probability adds up to 1. So Venn diagram can help us understand these formulas. But if Venn diagram doesn't help you understand, what's important as we go on the formulas is that you know how to use the formulas in a given context. Okay, so let's start the notes. Addition rule and the rule of complements. So first, we're looking at events involving not. So if I want to find probability of something not happening, not occurring. Okay, so E not occurring, we denote with the C and the exponent, E of C, but we read it as E complement. So the probability that event E will not occur is equal to 1 minus the probability that will occur. So this is the basic idea right here. Probability of E complement equals 1 minus E, probability of E, which also can be written as we saw earlier with the Venn diagram, probability of E plus probability of E complement equals 1. And just using algebra, we can also write it as probability of E equals 1 minus probability of E complement. All these three formulas are equivalent. You need to know one of them, and you can subtract one in both sides to solve for one the other. So for example, here, if I want to find probability of E to the C, I can subtract probability of E both sides, then I get this formula. Okay, so all these three are equivalent formulas. So let's look at an example. If a probability of event A equals 0.35, find the probability of A complement. We know, in general, probability of A complement plus probability of A equals 1. So we know this probability, so we want to know this formula. Oh, sorry, excuse me, this probability. We know this is, I wrote that backward, didn't I? We want to know this one, and we already know this probability is 0.35. So probability of A of C equals 1 minus probability of A. Probability of A is 0.35. So this is 1 minus 0.35. which gives us probability of 0.65. Let's look at second example. Similar. If probability of B complement, probability of B not occurring is 0.17, find the probability of B occurring. So again, same idea. Probability of B complement plus probability of B equals 1. We know this one, 0.17. We want to know this one, probability of B. So probability of B equals 1 minus probability of B complement. Probability of B complement is 0.17. So subtract that, we get probability of 0.83. Next example. Sample of 700 batteries were selected. Exactly 24 of batteries were defective. What is the complement of the defective batteries? So let's organize what we have. 24 batteries. Not defective batteries, which we can find by 700 minus 24. We have total of 700 minus 24, which is defective batteries. Then we get not defective, 676. Pay attention, in this problem, it did not ask for probability of complement of defective batteries. It asked just the complement. So if you were to find the probability of D complement, we just do 676 divided by 700. But again, in this problem, they didn't ask for probability. We're just practicing the concept of complement by itself. Let's look at event involving OR. So if you have a probability problem that says OR, probability of event A or event another event, this is the idea we need to understand. So previous example showed that we can approach finding a probability of an event indirectly by considering finding complement of an event. Another indirect approach is to break event into simpler component events and use the additional rule. So when you see OR, we're using the additional rule. Okay. So first, let's look at mutually exclusive event. Two events are mutually exclusive if they have no outcomes in common. Mutually exclusive events cannot occur simultaneously. So what are some examples? We'll do more example later, but to give you a quick example, we can when rolling a die, we can think as event A as a rolling an even number, event B as rolling an odd number. And in that case, event A and B do not have outcome in common. So what are some examples of not mutually exclusive? Well, it could be event A be a rolling an even number, event B could be rolling a number less than 3. Then it has a common element of 2 in that case. Okay, so we'll look at more examples, but just keep that in mind that not all events have something in common, right? So if A and B are any two events, then following holds. So when we find the probability, let me write the formula here, probability of A or B. And in math, in order to write a symbol for OR, we also use the union symbol. Probability of A union B. So this union means OR. Equals, and this is not letter U, this is symbol, probability of A plus probability of B minus probability of A and B. So this symbol is N. So why does the formula add two separate probability and subtract A and B? Let me draw a quick Venn diagram right here. So there's a Venn diagram of event A and event B. And of course, we have universal set, everything that combines A and B and everything outside of A and B. So here, what we're doing is if I want to find probability of A or B, what I'm doing is I'm adding everything in A, all the possible outcomes, and I'm also adding everything in B. But when I do that, this overlapping part are added twice. That's why we subtract probability of A and B. Okay. If A and B are mutually exclusive, that means they don't have anything in common. They're disjoint. So then, what happens is if I find probability A union B, the formula is pretty the same, but what happens is probability of A and B in mutually exclusive, this probability is 0 when it's mutually exclusive because they have nothing in common. So if I draw another Venn diagram, there's disjoint or mutually exclusive. They don't have anything in common, so we don't have to subtract any overlapping part. So it is important for us to distinguish when we solve a problem with the addition rule. Are they mutually exclusive or not? So let's look at some examples. If one number, we're selecting only one number from the set 1 through 10, find the probability of each of the following events. So here, we're finding probability of numbers odd or multiple of 4. So we have two events and it's or. That means we have to use rule of addition. Now we have to see if they're mutually exclusive or not. So one way to check that is we list all the possible outcome or sample space for each event. Number is odd. What are some odd numbers? Here, 1, well, all the odd numbers, 1, 3, 5, 7, and 9. And multiple of 4. Multiple of 4 is 4 and 8. There are no overlapping numbers here. Therefore, the way we find the probability, let me write the whole formula here. Probability of odd, number being odd or multiple of 4 is probability of odd plus probability of multiple of 4. We don't need to worry about adding or subtracting probability of odd and multiple of 4 because there's no such odd number such that multiple of 4. So odd, we have total 5 numbers out of 10 numbers plus probability of 4. We have 2 numbers, multiple of 4, out of total 10 numbers. So the probability is 10 over 7. Oops, sorry, I meant to write equal sign here, which is 0.7. So let's look at second example in same context from number through 1 through 10. Find the probability number is even or multiple of 3. Remember the general formula for probability of A or B is probability of A plus probability of B minus probability of A and B. So we can think as event A as even, event B as multiple of 3. So let's list all the elements. So what is event A's sample space? I'm going to list all the numbers. Well, even numbers. 2, 4, 6, 8, and 10. Event B, the multiple of 3, is 3, 6, and 9. Now let's think about this. What is A and B? Again, this symbol means and. Do they have any overlapping part? They do. The overlapping part is 6 right here, right? So we list 6. So we found the probability of each of these looking at these sample spaces. So here, probability of A, we have 5 numbers out of total 10. So 5 over 10. This right here is probability of B is 3 number out of 10. And A and B, there is 1. So A and B, probability of A and B is 1 out of 10. So when we find the final answer, what we have to do is following this formula, probability of even or multiple of 3 is probability of even, which is 5 out of 10, plus 3 out of 10, probability of multiple of 3, minus probability of 1 out of 10, which gives us 7 out of 10, which is 0.7. So the main idea here is that 6 was counted for twice. That's why I have to subtract once here. So in this case, these two events are not mutually exclusive. Let's look at this example. Amy plans to spend 1 to 6 hours on homework. If X represents number of hours to be spent on a given night, then the probabilities of various values of X round to nearest hour are shown in the table below. Find the probabilities that Amy will spend each of the following amount of time. So in this table, it's a probability distribution. And of course, probability is already given. So let's just review how to read the table. This is saying the probability that Amy will spend 1 hour, 1 hour is 0.05. Probability of spending 2 hours is 0.1, 3 hours, 0.2. So that's what the table is telling us. So probability for each X value is already calculated. But what we want to find is probability of finding or probability that Amy will study fewer than 3 hours. Well, fewer than 3 hours means 1 or 2 hours. So we're adding probability of 1 plus probability of 2. And there's no overlapping here. Right? Events are mutually exclusive in this case because it cannot be 1 and 2 hours. So we add these two numbers. I'm getting these numbers from here, and I get 0.15 is the probability that Amy will study fewer than 3 hours. How about more than 2 hours? More than 2 hours means 3, 4, 5, and 6. So 3, 4, 5, and 6. So we can add all these numbers. Okay. So let me write that. So I add all these numbers, then I get 0.85. But we could have also used the idea of complement here. Because we know fewer than 3 hours, we want to add all these, right? Adding all these is same as 1 minus adding these two. So using complement, we could have also done 1 minus 0.15, which would give us 0.85. Same answer. Either one's fine. And we do have to pay attention to the wording. More than 1, but no more than 5 hours. Right? So more than 1 means 2, 3, 4, no more than 5, so 5 is included. So we're adding, let me use red, these 4 numbers. So we add all of them, and let me write that, and we get 0.8. Fewer than 5 hours. So let me raise this to look better. Fewer than 5 hours. Again, it's a good habit to list actually all the hours. Fewer than 5 means 1, 2, 3, and 4. So we're adding all these 4 numbers. Okay, so probabilities. Then if you add all of those, you can check yourself. You get 0.75. 6 or fewer hours. Again, practice listing all the hours. 1, 2, 3, 4, 5, and 6. Because 6 or, so include 6 or fewer hours. So fewer hours or 6. That means actually all the probability. So we add all of them. Then we should get 1. Because probability of all this thing should be equal to 1. Let's look at an example using a standard deck of cards. Here's a diagram to help you visualize different suits and types of cards. So we have 8, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and different the suits, clubs, diamonds, hearts, and spades. So a total 52 cards. So let's look at the first problem, and I'll refer to this picture as I go over this example. Find the probability that a single card is drawn. So we would draw in one card from this deck of 52 cards. There will be a diamond or a face card. Face cards are Jack, Queen, and King. Jack, Queen, and King. You can think as this Jack, Queen, and King have faces on their cards. That's why we call it face cards. So here we have 2 events. Event A, diamond, or face cards, event B. So let's count how many are there. Number of diamonds. How many diamond cards are there? So diamonds are here. We have total 13 diamonds. Okay, so 13. We have 13 of them. How many face cards are there? Face cards. there are total 12. 3, 3, 3, 3. So we have total 12 face cards. So what we're doing is we're adding, let me draw it here, all the diamonds right here. And we're also adding all the face cards. But as you can see, when we do that, we're adding these 3 cards twice, the overlapping part, because these 2 events are not mutually exclusive. So overlap, there are 3 cards. 3 cards. We're adding diamond, jack, queen, king 2 times if I add these 2. So we need to subtract that when we calculate probability. So probability of diamond or face card, let's call it FC, equals probability of diamond plus probability of face card minus probability of diamond and face card, because we can have diamonds or face cards, as we saw, jack with king. So let's calculate each of these. Well, diamond, there's total 13 out of 52 cards. For face cards, there are 12 out of 52. Diamond and face cards, there are total 3. So we calculate this, we get 22 out of 52. So that's the probability. So it's important to pay attention. And a lot of times the problem itself will make sense or not make sense, depends on the events, if it's mutually exclusive or not. Here it is possible to have a diamond and face in context. But for example, diamond and spades are not possible. They're not mutually exclusive. So what's the probability of diamond or spades? We just add 13 plus 13 because we cannot have diamonds and spades. Nothing to subtract. But it is possible to have diamonds and face cards. Of 20 elective courses, Emily plans to enroll in 1, which she would choose randomly. If 8 of courses are recreational, 9 are interesting, 3 are both recreational and interesting, find the probability that the course she chooses will have at least one of these attributes. So what do we mean by one of these attributes? This is saying recreational or interesting. Either or is fine. So it can be both recreational and interesting, or just recreational alone, or just interesting alone. Okay. So essentially, we're finding probability of recreational or probability of interesting, which same formula, probability of recreational plus probability of interesting minus probability of recreation and interesting. So this is out of 20 elective courses. How many are recreational? 8. So 8 out of 20. Just interesting, 9 out of 20. And overlapping part are 3. So if you calculate this, we get 14 out of 20. So that's the probability that the course Emily chooses will be either at least interesting or recreational. It could be both, but it's guaranteed that at least it will be interesting or recreational, one of them. And the probability is 14 out of 20. Just a quick note, probability, as we saw earlier, is always between 0 and 1. So this fraction or the number we get should be always between 0 and 1. So let's look at a problem, another problem. If probability of A is 0.3 and probability of B is 0.4 and probability of A and B is 0.2, find probability of A or B. So remember, this and is this symbol, and or is union. So using the same idea we've been doing, we know that probability of A or B is probability of A plus probability of B minus probability of A and B. So here, all other values are given. A is given, probability of A is 0.3, probability of point B is 0.4, minus 0.2. Out of 800 large purchases made at computer retailer, 336 were personal computers, 390 were laptop computers, 66 were printers. As a part of an audit, one purchase record is sampled at random. What is the probability that it is not a personal computer? So here we're practicing the idea of complement. If you let event A, it would be a personal computer. Not a personal computer, we're finding A complement. So you want to find probability of A complement. That's what we're finding in this problem. So let's just calculate number of not computers, not personal computers. Number of not personal computers. Let's write PC. Personal computers. Well, we have total 800 and number of personal computers is 336, so we just subtract. So then 464 is the number of not personal computers. So if I want to find this probability is number of not personal computers divided by total number of items, purchases, which is about, or this is exactly 0.58 is the probability. So this is the idea of complement.